Take 3. Welcome to the third attempt to do the conjugated diene edition of HBr. It was a train wreck earlier today for reasons that I'll go to in just for a second, but it was a train wreck a second ago because I just spent 5 minutes drawing on my iPad without having that on the screen. And so that's going to be funny when I review that poor version of the video. It's late. I'm tired. I've been in a really deep rabbit hole when it comes to this particular topic, but I wanted to get this video out so that I can clear up all the misconceptions that mostly that I caused earlier today. It's all started out when we talked about the addition of HBr to conjugated dienes. We started out real nice with an example of butadiene and how the addition of HBr can proceed with that particular reaction. But then we got bogged down really quickly because we moved on to an example, and that we tried to use this. We tried to talk about thermodynamic versus kinetic control with that first example, but the problem is with that first example, it wasn't a symmetrical conjugated diene. And so if it's not symmetrical, it actually leads to 4 total products from two different allylic cations, not to mention the products from the non-allylic cations. And so at the end of the day, what we want to do is we want to go back to that. Let's talk about the simple example first, then let's immediately talk about thermodynamic versus kinetic control. And then let's look at some of the examples that are unsymmetrical and try to sort out how that actually looks on an energy graph and see why it gets convoluted really quickly. When you have more than 2 products, then especially if they come from 2 different intermediates, you start to get confused about where the different energies goes of the intermediates and the transition states because you don't have actually any idea about where they are and if they cross each other. And so I did a quick, I'm a computational chemist by training. I'm not an organic chemist. I didn't spend any time in the chemistry lab mixing chemicals. I did it all with computers. And so I do still have some tools at my disposal as far as that's concerned to do calculations and actually get energetic values, like actual numbers for the absolute energies of some of these molecules. And I did that for the 2 cations that I'll show you later. And I'll bring that into it, and I'll draw the most accurate back of the envelope reaction coordinate diagram for an unsymmetrical conjugated diene so that you can see, even in the most accurate situation, after doing a calculation based on quantum mechanics, that it still is a little bit confusing. And maybe one day I'll try to do a more sophisticated calculation that really tries to pinpoint every single point on the graph, but that'll be for another conversation. Okay, so let's try this again. Let's switch over to the whiteboard, see if I can, and let's start talking about this first conjugate addition. Oh, it worked. Okay, so I'm not going to redraw what I had on there now, but this is where we started. We're talking about butadiene and the addition of HBr, and the mechanism goes like this, right? The pi electrons come out, proton transfer, the bromine comes off, and then we have nucleophilic attack to the cation. There is another one over here, C. I didn't show that possibility. You could have the carbocation form in an isolated fashion here, and that would lead to a product like this. But at the end of the day, these products are not going to be predominant because of the formation of an isolated primary carbocation. The activation barrier for that reaction would be extremely high. And so that's not going to happen. And so let's take a look at the 2 carbocations that do form. And I say that there are 2 because it's we get to the point where we do a lot of reaction mechanisms year after year, and we draw these resonance structures, but we sometimes forget, I certainly do, that they're really not two different structures. It's really just one different structure. And our stick pictures or Lewis structures, they're just not sufficient to describe this situation. Remember that it's actually one structure with some partial positive charges in both locations. But we can think about it this way. And when we have if I have bromine attack where A is, and I'm going to erase them. I'm going to erase this one because this arrow was for the mechanism for the interconversion between the two resonance structures. When we have A, we get this product, and when bromine attacks B, we get this product. So this is the 1,2 adduct for that leads from product for A, and B is the 1,4 adduct. Now, we know from experiment that the 1,2 adduct is the primary product, and when I got down into my deep rabbit hole, actually the explanation for this kind of came out like in 1979. There's a Journal of American Chemical Society paper. I'll try to post it in Blackboard so that you can see that this question is essentially 50 years answered. But essentially what we're saying is that even though B, the 1,4 adduct, is the lower energy product, and we know it's lower energy because it's got the more conjugated double bond, there's something going on with A that allows it to form faster. Thus, if it forms faster, or if it's the more primary, if it's the predominant product, it forms faster, and then we can say, well, it must have a lower activation barrier. And so it's not that we knew that it had a lower activation barrier, it's that we knew that it was the primary product at cold temperatures. And so we said, well, if it's the primary product at cold temperatures, it must be the kinetic product. And so if it's the kinetic product, then it must have a lower activation barrier. And that's where we really start. We start with it not from examining the structures and trying to decide what's the different heights in the activation barrier. We decided, let's make the reaction cold, see what the predominant product is, then call that the kinetic product, and since it's the kinetic product, say that it has the lowest activation barrier, and it must form the fastest. And so it's sort of going the other direction. So we want to make sure that we explain this, and I'm going to explain it a little bit more in just a second. We're going to talk about it, and it really is this idea about the proximity effect. And it is the proximity of the bromine being close to where the cation forms. It's an ion pair. And so the bromine doesn't then have to travel to the end of the molecule to then add there. And so it really is just reacting faster because of that reason. And so let's think about that now just a little bit more deeply, and I'll just kind of draw another version of it. This is what we were saying here. If we are going to add the hydrogen at the end of the molecule, then maybe it arranges itself like this. This would result in this ion pair. So when I got into it and thought about it, I mean, even one of the most recent organic chemistry textbooks had to issue errata because they didn't quite have the explanation about proximity effect right. So I don't feel so bad if you're making some money on these textbooks and you don't have it right either, just like I didn't. But at the end of the day, this is what's going on. Once this first step of this reaction takes place and HBr donates its proton or does the proton transfer, the bromine's still sticking around there. And I guess I should have known that from my explanation about the stereochemical outcome of substitution reactions back in Organic Chemistry 1, but it's hard to put all the pieces together sometimes. And so because this bromide is still hanging around, this reaction that forms the 1,2 adduct happens quite quickly. And so what we say is because it happens quickly, it must have a lower activation barrier. we can't invoke the Hammond postulate for that because the Hammond postulate leads us to a different conclusion. So that's what I want to just kind of say about what was going on earlier today. Okay, so let's talk about what this looks like from the perspective of a energy diagram. So let's draw a reaction coordinate energy diagram. And I always assume folks know this, but I guess I don't remember that. They don't all the time. This is an energy graph versus reaction coordinate. So the x-axis is forward in the process of the reaction, and E is free energy. Okay, and so we're dealing with the same level of product, and it forms the same carbocation intermediate. All right, this is what we do know. We do know that, and I'm going to start to color code things now. We know that B is lower in energy than A. This is what we know. But what else we know from experience is that A forms faster due to the proximity effect. And so that means that A must have a lower activation barrier than B. Okay, so let me label some of the parts of this graph so that we're absolutely on the same page. Here is the activation barrier, the activation energy that leads to A. Erase this one. And this one is the activation barrier that leads to B. So the activation barrier that leads to B is bigger because from experimental evidence we know that A forms faster. So it must have the smaller activation barrier. Now, let's talk about thermodynamic and kinetic control. And I want to use that space here and let's talk about it. Thermodynamic control this is where the relative distribution of products is controlled by the energies of the products. Kinetic control is product distribution controlled by how fast one product forms compared to the other ones. Okay, and so we said that if we have cold temperatures, we know that A predominates, even though it's not the lowest energy product. It's not the one that's thermodynamically favored. And so why is that? And I want to go back to this graph that reminds us what happens at different temperatures. So what I want to do is I want to draw a graph like this. So in this case, the energy of activation is on the x-axis, and on the y-axis, it's the fraction of molecules that have a particular energy. So if I have T1 and T2, and T2 is greater than T1, let's color code it. Then this is what happens to the distribution of energies of the molecules in a collection of molecules. So this graph at the bottom shows you what the distribution of energies is in any collection of molecules at a particular temperature. Since I've drawn two different curves, I've got two different temperatures represented. I've got T2 and I've got T1. Okay, and so if we have some arbitrary activation energy, let's call this one R activation energy for our reaction, what happens? Well, only this proportion of molecules has enough energy to overcome the activation barrier. If I have the same activation energy and I just have a higher temperature, then all of a sudden the proportion of molecules that has enough energy to overcome the activation barrier has gotten larger. And we can tell that because the area under the curve is larger. So this is how raising the temperature increases the rate of any particular reaction, because the number of molecules that have enough energy to get over the activation barrier goes up. And so how does this affect the relative distribution between two separate pathways? Well, if I'm at a low temperature, I only have a low fraction of molecules that can get over any particular barrier. So the most molecules would be able to get over the smallest barrier. If I raise the temperature, then there's enough energy to get over both barriers, both this one and this one. But as I raise the temperature, now the reverse reactions start to come into play. And so if I were to think about the activation energies of the reverse reactions, there's this one, and there's this one. So as I increase the temperature, I start to have enough molecules that can overcome the reverse reaction activation barrier and reform the carbocation. Then if I had enough energy to go that way, then I certainly have enough energy to go back this way. So at the end of the day, when I raise the temperature and I give more molecules the ability to overcome any particular barrier, then the final product distribution will rest in the lowest energy well, period. However, if I lower the temperature and I restrict the number of molecules that can overcome activation energies, then the majority of molecules end up in whatever well has the smallest activation energy, because that's the reaction that's going to happen fastest at that temperature. And so this is what we mean by thermodynamic and kinetic control. In this particular case, on this particular energy diagram that's now got lots of different things sketched on it, there's only two products to consider, product A and product B. But once you have, and the reason there's only two products is because if I had HBr reacting over here, top left-hand corner, on the other double bond, I'm going to get exactly the same versions of the carbocation, and so I don't have to consider that set of products. But let's take a look at one where I do have to, an example where I would have to deal with a different set of products because it wouldn't be symmetrical. And so I think this is the example that I used before. It was this guy. And this is the one that I did a calculation on. Okay. And we're going to make an assumption. We're going to make the assumption that the proximity effect will have the same sort of effect on the respective activation energies of 1,2 adducts. And so let me draw pictures of the products that we don't even have to worry about at all because they won't form from allylic cations. I could have this cation form, or I could have this cation form, in which case the bromines would add here and here. It's not going to happen, remember, because those two cations I showed you, they're not allylic. And so these guys are going to be the very minorest of products. And so I'm going to stop considering them all together. Okay, so let's consider what happens when HBr adds there. And HBr adds here. Get the same sort of mechanism going on. And we lead ourselves to these carbocations. And I need to draw that guy there. Yeah, I already drew this one wrong, so let me back up. Trying to fix this mistake. I've already made a mistake here. I should have drawn it like this. So now let's redo these mechanisms. Okay, that's better. That's better. Still need that double bond there. Okay, I think we got it now. This one and this one. Okay, got it. Okay, and so now we know that each one of these things has a resonance structure. This one has this resonance structure. And this one has this resonance structure. And so it leads to the first set of products. And so I've got this product. This one would be the one where the bromine was already there due to the proximity effect. I get this product. The bromine adds here, had to move around. I get this product. The bromine adds here, it was already there, and I get this product. Bromine adds here, it had to move over there. And so I'm just going to arbitrarily call this A, B, C, D. And so I want to shrink it down so we can see what's happening. But let's examine what's going on. A is 1,2 adduct. B is 1,4. C is the 1,2 adduct. And D is the 1,4 adduct. So we think that the 1,2 adducts would form faster, and we think that it's going to do that through proximity effect. Now, let's start to illustrate how a reaction coordinate of this type of reaction, where there's 4 products, actually starts to get a little bit difficult. Okay, we start off with the same reactants, but we have a different set of carbocations. We have the AB set and we have the CD set. And here's the very first problem. Which one's lower in energy? The AB carbocation or the CD carbocation? And remember, the set of carbocations is represented by these resonance structures. These resonance structures. And so examine those resonance structures. Pause the video and see if you can sort out which one is lower energy, AB or CD. This one being the CD and this one being the AB. Okay, let's take a look. How would you decide? Well, you could look at the number of substitutions in the double bond that's still there. In the AB, you've got 3 substitutions in both versions of the resonance structure. And in CD, you've got 3 substitutions in one version, but only 2 in the other. However, in CD, you have tertiary and allylic cation on one and secondary and allylic on the other. But in AB, it's only secondary and allylic in both cases. How do you know right now which one of these is lower in energy? Did I put the blue one for CD, or is it in the right place? How would you know? And the bottom line is you probably wouldn't. And so this is where I actually did a calculation. It turns out that at the level of theory that I did the calculation, the CD carbocation is about 35 kilojoules per mole lower in energy than the AB carbocation. And so it turns out that that tertiary allylic position really is the predominant factor here. And so what we're going to do is we're going to use the Hammond postulate to sort out those transition states. We're going to say that the transition state leading to AB is higher than the transition state leading to CD. Okay, Now, let's do the products. This is where things really get to be a challenge. All right. Take a look at the products A, C, D, and B. The product C has a double bond that is di-substituted, but A, B, and D have tri-substituted double bonds. They have tri-substituted double bonds, and the bromine is one removed from a tertiary position in A and B, and one removed from a secondary position in D. So that, again, in that case right there, just that one little difference, the little difference that this bromine is one removed from a secondary position, and these bromines are one removed from a tertiary position, means there's going to be an energy difference. I didn't do a calculation here to determine what the actual energy difference is, but at the end of the day, they're probably pretty close in energy. They're probably pretty close in energy. So even if we just said it's A, B, and D, all in the same energy level, we're still going to have some problems later. Let's go on and hold on for this for a second. C has a di-substituted double bond, so it's higher in energy. Again, we don't know how much higher. Okay, now let's go back and look at C versus D, because now we want to draw the transition state between C and D and the two products. Well, we're going to say because C is the 1,2 adduct that formed faster because of the proximity effect, that it's going to have a lower activation barrier than to D. For the same reason, we're going to say that A has the lower activation barrier compared to B. Whew, look at that mess. And so here's the thing. What we don't know is we don't have any idea if we got this correct, if the overlap here is right. Maybe the activation barrier, the actual energy of the transition state leading to D is lower than the activation of the actual energy of the transition state leading to B. We didn't do a calculation, we don't know. So here's an example of a convoluted situation. Here's one thing we can say. C is probably the kinetic product. And the reason we can say that is it has, in both cases, the lowest activation barrier. So it'll predominate at cold temperatures. What we don't know is what products will predominate at higher temperatures, because we already know that we got this wrong. On top of that, we don't actually know what the difference in energy is here and how much temperature it would take to overcome that, just that difference. And so so I'm going to leave it there, and I'm going to say this is an example of a situation where it's not perfectly clear what is kinetically controlled and what is thermodynamically controlled. And so when you get a question like this on an exam, I'm going to give you one that's symmetrical so that you don't have to go through that process. I'm going to make sure that you can do it and actually come up with an answer. If I were to give you one where you'd have to do a convoluted energy graph, then it wouldn't take much to get to the full credit level, because I'm really going to look for you to start to struggle. And once you reach the level where you're starting to say, well, I really can't tell the energy difference between this and that, then I say to myself, well, that person really has all of organic chemistry 2 at the sophomore level figured out, because I can't tell, and so they can't tell either, and they know they can't tell, and so they've reached the pinnacle of learning for this particular section. And so we're going to leave it there. And so there's going to be 2 different types of products and 2 different types of problems in summary. Addition of conjugate diene addition on symmetrical dienes that will lead to only 2 products, and conjugate addition on unsymmetrical dienes that will lead to 4 products. Now, remember, I'm still not talking about, in the first case, the product from the isolated primary carbocation that we don't even count, and the same thing for the next example. I'm not counting any of those isolated primary or secondary carbocations that form. I'm only talking about products that lead from allylic cations. And so that's going to be your challenge, is to sort out the difference between those 2 things. When it comes to thermodynamic and kinetic control, it's going to be symmetrical. When it comes to what are the products, then it can be either one of those versions. And so I hope this does some justice in clearing up the confusion that I caused in my train wreck earlier in class. And I think then what we're going to do is we'll leave it here. I will post this tonight before I go to bed. And then tomorrow I'll start and I'll create a Diels-Alder video, and I'll create an there's one other reaction I'll create a video for. It's slipping me at the top of the head right now. And so I'll post those so that you can study this weekend. I've got some practice ready to go for all of this stuff. And so we'll hit the ground running on Tuesday, and we'll just do practice on Tuesday. All right. Good night, guys.